Ready to rock and roll? Okay.
Well, it's when you're on. Great.
Okay, well, let me welcome everybody to the third of the Montana Nanotechnology Center webinar series. And this is a project sponsored by the National Science Foundation and the National Nanotechnology Coordinated Infrastructure Network. Today we're going to hear from Dave Dickensheets and Phil Himmer about the Montana Microfabrication Facility. Before we start, just a little bit of homework. First of all, welcome to the people out in the world. Thank you for joining the webinar. If you would like to ask questions, you can do so with the chat function that should be on the side of your screen. And we will stop midway through the talk and take questions. For those of you in the room, if you want to ask questions, there are microphones on the tables. Please leave those off during the talk, and when we have the question and answer period, if you just have the microphone right in front of you to have your questions recorded. So one other thing is we really would like you to fill out a webinar evaluation. For those of you in the room, we have hard copy, and for those of you out in the ether, we have a link from our webinar website. Just click the link. It'll only take, what, 3 or 4 minutes, Carolyn? Just a really short survey just to give us some feedback on the webinar and what other things that you'd like to see. So with no further ado, here's Dave Dickensheets and Phil Himmer to talk to us about the MMF.
Thank you, Dave. So thank you all for coming, and we're glad to tell you a little bit about the Montana Microfabrication Facility. Again, I'm David Dickensheets. I'm a professor of electrical and computer engineering. I'm also the director of the MMF.
Yeah, I'm Phil Himmer. I'm the manager of the facility.
So we're going to trade back and forth, and each of us is going to give some different bits of information, but the objective here is to try to convey to you a sense of what's possible to build in the realm of micro and nano devices and structures in the MMF here at MSU. So I'd like to start by just acknowledging the support that we've had over the years to build and sustain this activity. Dave mentioned the NSF program, the NNCI, National Nanotechnology Coordinated Infrastructure Program. That's funding this webinar series, but it also is providing baseline support for our facility. I'll say a little bit more about that as we go through the talk. I'd like to acknowledge the Murdoch Charitable Trust, several federal agencies, National Science Foundation, SBA, and NASA, who are the primary sources of funding for the equipment in the MMF and also user support. The Montana Board for Research and Technology Commercialization has helped us through user grants for our industrial users. They've also been supportive of several of our users through direct grants. The Micron Foundation and SemiTool have provided key instrumentation, and then institutional support from Montana State University, from the College of Engineering, and from the Office of the Vice President for Research. So just want to be sure we acknowledge the generous support from those entities. So by way of outline, I'll start with a bit of an overview, and we thought we would share just a little bit of the evolution of the MMF from its inception until today, and talk a little bit about research, but also the impact that the MMF has on education for students and users here at Montana State. And then Phil will give us an overview of the tool set that's in the lab, and we'll take a little break about halfway through to answer some questions. And then we're going to give some examples of some projects and try to give you convey a sense of what's being built here and the expertise that has developed around that. And then talk a little bit about coursework, training, some new capabilities, and a little information about how you can get involved as a new user of the facility. So by way of overview, we mentioned MONT, the Montana Nanotechnology Facility. MMF is an entity within MONT. MONT is 5 user facilities here on campus. The others are the Imaging and Chemical Analysis Lab, ICAL, Center for Biofilm Engineering, Center for Bio-Inspired Nanomaterials, and the Metabolomics, Proteomics, and Mass Spectroscopy Facility. And so within that, MMF you might view as the micro-nano makerspace. This is where we are actually constructing nano devices, micro devices. And the MMF does that by hosting specialized tools that are in a clean room environment. So We've got filtered air to remove most of the particles, so it's a clean environment. It's also a controlled environment from the point of view of temperature and humidity. We're doing chemical processes, photolithography, that is much more stable if we can keep the temperature and humidity at a fixed set point. So controlled and clean environment is the foundation. So the MMF has been operational for a little over a decade here, but micro and nanotechnology in the Gallatin Valley is certainly older than that. People have been building micro devices. A couple of examples on this slide, optical MEMS devices that were not made at the MMF, that were made in the late 90s and early 2000s. Another example on the bottom of the slide is the structured nonlinear optical waveguides that ADVR has been working on for a couple of decades now. So this was work that was happening here, but there was no local facility for building these devices. So the researchers that were doing this work were traveling, and they were going to places like the NSF NNIN sites, Cornell, Santa Barbara, University of Washington. And so that was possible. We could use those sites, build these devices, but it was expensive, measured both in time and money. And because users would go there, you've got the cost of travel and housing in addition to the cost of using the facilities. We could get work done, but it also limited access for students here. So you pretty much had to be a PhD student and done with coursework so that you could afford the month or 2 or 3 or longer that it took to travel, get trained, do the work, and then bring your devices back to MSU. So motivated by that, we were able to assemble our first set of tools, and our first fabrication tool within the MMF came online in 2004, and that was a sputter station for depositing thin films, and Phil will show you that tool in a few minutes. So soon thereafter, we had tools for doing basic photolithography, that's the patterning of the wafers, thin films deposition, including the sputter tool, and selective etching, both wet and dry etching capabilities. And with the introduction of this capability on campus, we saw quite a bit of expansion of activity and opportunity for both research and for education. So the PIs were getting their work done, but also a lot more students now are being trained, including undergraduate and master students who wouldn't be able to travel and get the training remotely. So that's been a huge improvement for nanotechnology here at Montana State. So our mission within the MMF is to provide this local facility, local tools, but also the expertise and education of the users. The users are students, but also industrial users and those who are coming here from outside the university. But we also are affording a seamless access to this national network, this NNCI network. So we're part of this NSF program. There are 16 sites around the country, and we have users who are going to several of those sites. We also have users going to clean rooms, for instance, University of Utah or University of California at Santa Barbara, who are not in the network, but have tools and processes that we're familiar with. We can help connect you to the tools and the expertise that you need for your project. So we're the access point. So what's our philosophy for balancing what we have locally versus what we can access remotely? It's fairly straightforward. Those common processes that are applied routinely, often repetitively, in doing microfabrication, we've got covered here. So this is what users are spending most of their time doing, lithography, for instance. We also have basic education in clean room protocol and then training for the various tools that we have in MMF. So we do all of that education here. And then in addition to these common tools, we'll have a few specialized tools that reflect individual research expertise or needs for our PIs that are here local. That gives a little bit of local flavor to our facility that might make it look a little different than another basic facility. We find that you need to have good characterization tools locally and a little bit of packaging capability locally to build your devices. Access to CAD tools for simulation and to draw your masks that you're going to use for lithography. And then, of course, expertise, staff expertise, and the collective expertise of our user base that make it so that you can be productive. On the other hand, there are tools like ion implantation or low-pressure chemical vapor deposition that are just too expensive. We don't have the volume of use here at this site to really justify that. Furthermore, those are processes that it's easy to send a wafer to a remote site, wait a day or two, get the wafer back and continue your processing here, or in some cases, maybe the user has to accompany the wafer to the site. I'll give a couple of examples of that. But then specialized processes through the network and through partnering with other institutions, a user here at MSU has access to comprehensive nanofabrication capability by partnering with these other institutions. So we'll help make those connections. And increasingly, I think computational tools, even layout tools, are going to be cloud sourced. It's going to be a lot easier to do that as a networked resource as opposed to needing to maintain all of those software tools here locally. So I'll hand over to Phil now, and he's going to give you a walkthrough of the tool set within the MMF.
Okay, so hi. So on this slide, I have the tools, most of, not all of them, but most of them broken up into 6 categories, kind of lumped together by process. So these are systems that you use together to get accomplish a certain process. So I'll start in with photolithography, which is probably the most fundamental process that is needed. Very quickly, tools to go through some of the usage. A vapor prime oven for adhesion promotion. It's very helpful to have your photoresist features stick to your substrate. So it's a pretty common tool. Spin coaters for casting the photoresist. These are all photosensitive polymers in a solvent solution. So we use spin coaters to cast those, although we've now acquired a new tool, which I'll talk about in a bit. Contact aligner, which is we do to transfer the pattern from your mask that you'll make with the CAD program into your photosensitive material. Then we have ultrasonic cleaner for cleaning the masks. These are some basic tools that you can use to get through this process. For example, have a 7-micron grading shown here in photoresist on SI wafer, silicon wafer.
0.7 micron.
0.7 micron, excuse me, thank you. And just to point that, so we claim that we can do 2 micron features, and that's kind of what we'll say we can always do no matter what. You can do better, you just have to work at it a little bit. And you are limited in kind of what kind of structures you can build at, say, 0.7 micron, but you can do better than 2 micron if you need to. And take note that the sidewall, ideally you want a perfect 90-degree sidewall. This is pretty close in this picture. Down below we had lithography done where we actually got, I think, very close, if not right on 90 degrees. That's important for transferring your patterns correctly. So I talked about spin casting. One of the issues, and here's a short little video of Su8, which is it's a photoresist. We call it an epoxy. It's photosensitive epoxy. It's a negative resist. And one of the problems with this is this resist spins probably about 1,000 RPM. You see the color sweeping over the wafer. So it's a transparent material. It's visible light, and you'll see the color has to do with the thickness of that film. And if you look carefully, you can see, you still see a color variation across that surface. You're spinning films this thick, it's very difficult to get good uniformity. Because of that, we have recently implemented a Su8 lamination system. We've, in the last couple of years, companies have started selling commercially films of this type of negative epoxy already made, pressed into a laminate material, so it's not in solution anymore. So you can actually put your wafer and laminate this layer of film on top of it. The uniformity is much better from their manufacturing process, and it also allows you to have much better results when you're doing tinting, which is basically you're covering over already structured features where you have big holes or vias or voids. You can actually put this material over the top of that and start building three-dimensional structures a lot bigger, with a lot bigger spatial features than you could otherwise by spin casting.
Ask questions.
Uh,
Because I was going to ask about that video.
We'll come back to that later.
Can you save it? And we've got a little pause in the middle, and then we'll catch all the questions at that point. Thank you.
So the second section of tools is the PVD physical vapor deposition. This is how we deposit thin films in our facility, both metals and dielectrics. This is, I think, in the thin film community, a well-known diagram by Thornton from the 1974, and it was actually done earlier by some other people, different variations of it. And then really the main point of this is to show that these films, independent of material, the structure of the film is dependent a lot on the process parameters. And so you're never gonna, so that on this axis is your temperature, 1.0 is melting point of the material you're trying to deposit. And this is specific for sputtering. You have argon pressure on this side. Thing to note, we typically operate in zone 1 to zone T, maybe get into zone 2. But it's very difficult. We don't, depending upon what tool you have, you get limited to where you can deposit materials, what kind of morphology you can get. Recently, with the addition of ion-assisted deposition and high impulse magnetron sputtering, they have been able to, now you have ion impacts with this deposited film, and so you can get densification of films. You can actually go into etch regions of the film. So they've, with different tools and different capabilities in your tools, you have a broader area of crystal structures or polycrystalline structures you can get with these films. So these are not like a bulk grown film at all. So your properties depend a lot on the process deposition parameters more as much as the material itself. For one example, we have a thermal evaporation tool. It's just for aluminum. We use this mostly for coarsework, but some meters use it also for electrical contacts. Simple to operate, inexpensive to operate, suffers from poor uniformity, and you don't have any rate control, which is a detail that, but for electrical contacts, it's not really that important. So it allows us to have classes come in and do a lot of deposition work. A couple of wafers, a photovoltaic wafer that the class had done, and here's one with some transistors on it. Just the type of tool they would use to get these metallized layers on their wafers. A little more sophisticated tool, significantly more in fact, is called an AMOD, electron beam thermal evaporation system. It's tool's computer controlled. It has rate control. And instead of just having a way of thermally heating a material with tungsten filament, it actually has a source of electron current, excuse me. So you can, in this case, from the picture from left to right, you have electrons coming out from underneath from a filament. Magnetic field turns that current into a target of material. So down here you see a nickel material that's been melted that you would use then as your evaporation source. So you could heat, in this case, with the electron beam, you can get high enough temperatures, you can actually melt silicon dioxide. We don't melt it, sublimate it, but you can evaporate silicon dioxide, aluminum oxide, magnesium fluoride quite easily. Also have two thermal sources in the tool, mostly for metals. For different reasons, you'd want to use this source. So one example of a deposition, a researcher at the university working at the mass spec lab, in fact, has needles that wanted to have a electrical coating of gold on the tips so they can do ionization of, I think, large molecules. I think anyway, and then on the side here, you see them in the tool itself is this needle suspended down to where they would eject the liquid out of. This is the kind of thing we can support quite easily with our staff and our equipment. Next tool is Angstrom sputter system. Unlike the evaporation tool, you don't heat the target material directly, get vapor coating your substrate. In this case, you actually hit your target material with argon ions, and they ballistically eject that target material out into the chamber, and then that coats everything in the chamber. Over on the right side, we have two RF sources and one DC source inside the system, so you can run all of these independently or at the same time, depending upon what you're trying to deposit. This tool, again, just to go back to that structure zone diagram, you can see here this aluminum coating, and there's just by changing the pressure from 2.5 toward the 10 toward, you get a much different surface. It's probably not so easy to tell on the photograph. A little bigger, higher magnification on the electron microscope to see this more clearly, but you get a much different film. It'll have different conductivity and mechanical properties. Another example here is a sputtered co-deposition. We had two guns running at once for magnesium and titanium to make an alloy, and I'll discuss that a little bit later. So moving on, furnaces, another way, not so much to deposit, you can grow oxide into Si. Silicon basically grows glass on the surface of the wafer. And it's one way, that's a standard material used for insulation. And we also have, besides this one, which is somewhat programmable and computer controlled, we have a manual oxidation furnace, and we have two furnaces for doping, both boron and phosphorus. This supports our class transistors and photovoltaic processes, so you have active devices in this case. And then dry etch tools. So you lay down your layer of thin film. Now you want to pattern it. And you also need to remove the photoresist and sometimes clean up some polymers. So we have this case, a microwave plasma etcher. It has oxygen argon in it, and it's just for removing photoresist or other polymers. We have a March plasma etcher, where this is a parallel plate etcher. It has gases for silicon oxide, silicon nitride, and oxygen for, again, etching polymers or activating for bonding, activating surfaces, thank you, the surface. And then our primary etch tool is this ICP etcher, unducted coupled plasma etcher. As a suite of gases that we can do quite a bit of stuff, etch a lot more materials and have a lot of ways to adjust how that etch occurs. So we have a lot of process control with this tool that we don't have with the others.
Do you want to mention cryo as well?
Yeah, I don't have pictures of cryo, but we can cryogenically etch, which allows us to do some unique process things. You can optically smooth surfaces that are fairly large and in depth.
So we can keep the substrate anywhere from 0 degrees down to negative 110 C.
So we can go up to plus 200 C down to minus 110
as well
C.
as.
Yeah, so it just depends on what your process requirements are. And we have some processes that we know, and then what we don't know, we can hopefully help you find. There's some examples. Here's a MSU Bobcat that's probably around 100 nanometers, given what I can remember from it. Another one here is a little wave guides, light guides for, I'm guessing, infrared application. And this, I like this one because this is just grit. It's aluminum oxide from a polishing solution.
Slurry.
Yeah, it's a polishing slurry, dried it on the wafer, put it in, use the SI etch process. It's actually a 200 nanometer deep etch. You can see here, this is the top surface of the wafer. Then we etch down 200 nanometers. It's a little rougher, but it's hard to tell the difference. You can see how steep the sidewalls are. So anywhere where it's shadowed at all, it's very directional, and it's a very smooth etch. So that's at the nanoscale, we can do that. If you want to go all the way, wafers are 0.5 millimeter thick, all the way through it, we can use a Bosch, kind of a pseudo Bosch process, they call it, where you cycle between etching the silicon and passivating the sidewalls of the silicon. So you can just work your way through, and that's this scalloping features you see. So it allows us to do very deep etches. So just depending upon the needs, we have a lot of different tools or processes we can use for that one tool. Also support wet processing. All these substrates have to be cleaned before you can do a lot of these processes. So we have a lot of chemical baths, dedicated baths in some cases. Piranha, for this case, for removing photoresist. And we have also baths for etching oxides, for etching bulk silicon and tetramethyl ammonium hydroxide. Then we have the spin rinse dryer. It is a washer dryer. That's what it looks like. And we also have some decks, which is deck space where people do general beaker chemistry. It's a classic photo from a long time ago I found that shows, so you can go in and have some just general open space where people can do things that are not standard or set up for just routine processes. Also some characterization tools. Gonna hurry through here. Reflectance spectrometers to do some optical measurements, ellipsometer and reflectance spectrometer for the films. We have a stylish profilometer where you can measure and scan primarily one direction very accurately. In the second direction, you can step over and get a map of the surface. This is good 50 angstrom to hundreds of microns. Think of it as a very crude AFM, which can be sub-angstrom in resolution. This is 50 angstroms in resolution for its best case. Then we have a 4-point probe for electrical conductivity of your films. In addition to our tools, we utilize iCal a lot. As you've seen from the prior photos, we have a lot of electron microscope pictures. We also use the atomic microscope, the XRD, use the XPS a lot. I'll show some examples of that in a little bit. And they also have EBS, OJ, time-of-flight sims. And you can see more about iCal in the webinar they've done previously, and it's posted on YouTube, or it can be at the Carleton site.
So that was Recep and Dave who gave that a few months ago. So.
Yeah. And then finally, packaging and test. You can either, if you take your wafer, dice it up into pieces till die. We have a bonder. In this case, we're showing gold wedge bonding, where you can bond your die to an external package. Most of your computer chips, your IC chips, you're going to see this type of bonding you would have. I think technology is shifting a little bit, but for us, for our devices, this is the technique we have. or you can probe just at the wafer level a particular die or a device on the wafer using a probe station. Okay, so for doing all this, professional staff is myself. I have a half-time engineer, Jason, who does a lot of the tool maintenance, repair, enhancing the capabilities of equipment by building fixturing. And then we have a new engineer, Benjamin, who's lithography and helping with soft materials and microfluidics, where he has some expertise. And then I have a suite of students without whom we probably cannot run this lab. They're great help. Carrie, Dustin, Megan, Cody, and Trevor. So I appreciate their help every day. So that's it for the tool set. I guess the obvious question now is, okay, how much does it cost and how do you get in? So fee structure, we have a monthly access fee. This is just we set this per month to cover the cost of consumables. We go through gowns, all the wipers, but also things like water, nitrogen, HEPA filters. Some things are obvious to the user, some things are not so obvious, but it costs quite a bit to keep this kind of controlled environment clean.
And what's our access fee currently?
Currently, it's $200 for academic, $400 for commercial per month. And I think we have made special allowances for people who have very unique needs where they are only going to access certain portions or use a specific tool. So we can work with you to get you in the lab. And then we also have hourly rates. And so once you go in the lab, using each tool has its own hourly rate. Some, like microscopes, are free to use. Other things, like the IC etcher, cost quite a bit. It's expensive to maintain and keep running. So it just depends upon the tool. And then we do employ a monthly cap. This is $2,500 a month academic, $5,000 commercial. And that's basically if you're working full time in the lab, you can quite easily hit that cap in a couple of weeks. So we use that so that the expenses are predictable. And hopefully when you use things a lot and often enough, I think our budgeting is such that we think that will cover the operational costs.
And it helps the PI when they're writing a budget for a grant. If they can think about, I need 4 months of processing time, I can put in 4 times the academic cap or the monthly cap, and I should be covering the expenses fairly accurately.
So just kind of have some idea of limits on the expenses. And we do charge for some specialty thing like gold. If you want to deposit a lot of gold, you'll have to pay per gram, as we do. It is expensive. But then to help cover some of these costs, the tool charges and the access charges, we have user grants available for external first-time users of the facility, and David can tell you more about that.
Yeah, in fact, we'll reiterate that point again in a little bit. So, Regip, do you remember your question?
Yeah. I hope so.
Can you touch your microphone? It's this.
We don't have. There you go.
At the very bottom, it says push or press. Push.
Am I on? Okay. Can you go back to your the video? Okay.
Yes.
Screencasting.
You want to watch it again?
Yeah. No, I assume that round thing is the wafer.
That's the silicon wafer, 100 millimeter diameter wafer. That's our standard substrate size.
And so it's spinning is kind of distributing the code.
Yeah.
But I also heard you said you improved something. So I was trying to catch that.
this,
so I wasn't sure if it was related to this.
No, so the spin casting technique for these really viscous films is difficult to get good uniformity. And so
the thicker, more viscous films.
Yeah.
We have a hard time getting a uniform coating with spin casting.
Yeah. For example, user does films 25 micron thickness. For instance, we'll see plus or minus 5 micron variation, so significant variation. And if we go to these pre-made laminate sheets of material, thickness variation is 5%. So we're talking 1 to 2 micron variation in thickness. And so you can't in this pictures, it's really impossible to see the actual laminate sheet because they're basically discs of this material that are appropriately sized for the substrate.
I see.
So you buy these, it's more expensive, but for low volumes, it's
laminate.
the way to go because we don't typically have users that come in and make 3 or 4 wafers. And so they only need 3 or 4 pads. They don't need a quart to this material. The solutions are $800 a quart sometimes.
And then the next picture, please. After that, one more question, I'm done. Yeah. Tell me what you're doing here. I kind of didn't understand that.
We could spend the entire talk about this, this diagram. I know with you.
But this is polycrystalline structure.
Yeah, so this is basically kind of the structure of the film as it's growing on a substrate. So once you get over about 100 nanometers, you get these kind of film structures. And they have, some of them are very porous and have a lot of voids. Some of them kind of grow together in more of a polycrystalline amalgam, I guess you call it. And then as you go to higher and higher temperatures, you get more crystalline growth. And it has to do with the deposition parameter, the energies of the atoms hitting the substrate and the temperature of the film as it's growing.
But why is it you have a gradient?
Oh, that's just for viewing. That's just for visual.
That's for me. Okay, thank you. Okay, thank you. I'm done. Go ahead.
So tying into this Su8, I don't have a microphone. So
Oh, okay.
I have to repeat that. Tying into this Su8 laminate, you know, we tried up to 100 micrometers, and yes, we had issues with variations. What are the thicknesses that you can get, or can you layer different laminates above to get to this 100 micrometer thickness?
You can buy.
So the question is, what's the range of thicknesses for the laminated films?
So we've just started implementing this for about 2 weeks to a month now. I've seen anything from several microns to hundreds of microns available, depending upon what you want to do. There's two different types of materials, and we don't have a lot of experience yet with the thicker films, but with the sub 100 micron films, we're seeing good results. And so yeah, one of the things this person wants to do is just stack these layers together actually to build some pretty big structures. So, yeah.
Sarah?
Is it heated or something to help with the adhesion, or is it just room temperature when you do that lamination?
No, it's heated. The rollers are actually heated. Yeah.
How hot?
I don't. My lithography engineer could tell you. I don't remember.
Isn't it nice to be able to say that?
Yeah.
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 Do you have the laminate in-house now?
Yeah, we have some in-house that we're stocking, just the ones currently that people we know have definite interest in, and then as we'll just kind of feel out what the user community is interested in, and we'll try to carry some basics of thicknesses that people can use.
And then the pad that you laminate on.
Oh, that's your substrate.
Yeah.
It's just
What kind of thicknesses do you have for that?
just silicon wafers. What we're using. That's people
No,
using
but the
the
Su8.
Su8 thickness. I don't know the details of what's stock currently. I think it's 20 microns.
20?
Current pad
Okay,
thickness.
great.
But I'm not. Don't quote me on
But
that.
we were just saying we can purchase
Yeah.
those over a wide range of thicknesses.
Good. And then one more question. Last time I checked, the ellipsometer was not working. It's up and working now?
It does work. We'll take technical. These are lab. This is just an email about
Okay,
lab stuff.
okay. All right,
Sorry,
thanks.
not further talk.
It's not irretrievably broken.
Yes. It does
Okay.
work, but it needs calibration.
All right. Robin,
Can I ask one more question?
you can ask one more question.
Okay, so one of the things that we did was we now have a decorrective ion etcher, but we also bonded glass Pyrex cover slips for microscopy onto the Silica Waivers. Can we do that here, or do we still have to send that off?
Not yet. We still have to send that off. Well, actually, we're going to point that out to the next section of the talk. Yeah.
Oh, right. So
Oh.
the question again was about bonding. And in fact, we're going to address that question coming up. So we'll have a slide that has a picture of your device, actually. So this is bonding of glass to silicon. And we don't have a bonder that does that. We have high temperature furnaces, and we have ways that we could accomplish a bond, but
We have oxygen plasma.
there are better tools to use.
But for the wafer level, you need to use a tool to do it well.
So I am going to quickly highlight a few projects, actually Phil and I both, that will give users, especially those who haven't been in the clean room, an idea of the types of structures that people who are here, have been using the facility, are able to build. And this is intended to spur your imagination about what you might be able to do in the lab. So let me start out by just talking about some E-beam lithography. So Wataru Nakagawa is here in the room, and his group is engaged in designing and then building nanostructured materials for nanophotonics or nano-optics. And these are, we call form by refringent materials. By building a grating, we can put a lot of anisotropy in the material. We do it on a small enough scale, the sub-wavelength, we don't get diffraction of light. The light wavelength is too long to be diffracted. So we wind up with we call it a metamaterial. It's got an engineered anisotropy to the material. So what's required to do that, and what can we support? So primarily through the users from Dr. Nakagawa's group, working with the staff, we now understand how to build, for instance, a bilayer electron beam resist out of PMMA that gives you these critical undercut structures here. So these are little lines of PMMA, and this tapered structure here is important because we then do a directional deposition of a metal, which is a mask for a subsequent etch of the silicon. So that's deposited directionally from above, and with this undercut structure, you get a nice clean break between the masking material on the wafer and that's supported by this polymer PMMA layer. We come back through later and dissolve the PMMA, and all this other gold goes away, and we're left with the mask on the wafer. And then we use that mask in order to transfer the pattern into the silicon. So this is you can see the scale bar here, 1 micron. So this is nanoscale etching in the silicon. And once again, for these structures, they need this undercut profile on the etched features because they're going to once again deposit now a very specific layer of gold on the surface of the silicon to build this unique nanostructured optical device. So this is silicon. It's a bilayer grating of 2 different layers of the grating spatially separated in Z, and this gives the desired optical properties of those films. So these are processes now that we have in our toolkit that we can share with other users who need to do E-beam patterning. We can do basic E-beam writing over small fields here using the scanning electron microscope. Feature size is limited to probably about 50 nanometers repeatedly. If you need really precise electron beam writing, then we have, Wataru has sent students to the University of California at San Diego and maybe other places, and so we can put you in contact with people there, make that an easy process. So you want to talk about
Sure.
ADVR's devices?
So since the inception of the lab, ADVR has been one of our most active users. Part of the reason I think the lab was made with them, Paul Gannon, and a few others right off the bat, helping them with their processes. And it's fairly straightforward. They're building these waveguides, and they use our facility primarily just for masking materials and the pattern their masking materials. And they have multiple processes they use, but they'll use metal or silicon dioxide, for instance, as a dielectric, and pattern that to actually realize their devices. The materials they use are nonlinear optical materials. So it's not a standard fabrication material that you would find in most labs. That things such as potassium titanal phosphate, KTP, lithium niobate, or magnesium doped lithium niobate, or lithium tantalate even. And these devices are all used for optical sources. Excuse me. Just here a quick example. Waveguides here, you have a mask pattern, and here they actually have a mask for polling. And so they actually switch the electric field. These are ferroelectric materials, and so they have a polarization direction. And that plays into, when you process these materials, what kind of structures you can get.
It's also some of the challenge of working with these materials because they're pyroelectric.
Yeah.
So you've got put it on a hot plate and heat it up, and it's suddenly arcing.
Yeah,
and that does weird things to your photoresist.
And it breaks, and these are expensive. So you have to. There's just some details with these ferroelectric materials. One of the most interesting things we just found while we were playing with fabricating ridge waveguides was that it's just chemistry on the etch surface. It was very sensitive to the polarization and also any type of proton exchange where they swap lithium for hydrogen. And you see the etch depths are much different, the roughnesses are much different. So they're kind of a fun material to play with. But anyway, so it's some of the materials we do use in the lab, and we have some familiarity with how to handle them in the lab. Other things that we do, and this is probably more of where we're trying to support this new area, is soft lithography. In this case, Professor Makala has used Su8 as a mold or a master, and then made a mold with PDMS. And she actually makes these little reservoirs that contain a solution. In this case, I think for RNA or DNA, and a solution. Then once she fills these reservoirs, she backfills these channels here with oil, trapping the solution. And this here is a fluorescence image just as a test to make sure that fluid is in fact trapped in those channels. So it's just one example of some things that can be done in our lab, and some of this they can actually do in their own lab, but we do still support that process ability, which is part of our function. Another example, Dr. Chang I'll let David take over here, but uses the same type of process to do the micro droplets.
Yeah, so we call these soft lithography just because the materials, the ultimate material this is made out of is a silicone rubber. Essentially, it's PDMS, and so they're building a mask either in Su8 as a permanent layer, a permanent material, or they're etching these structures to build a mask. But then they can cast many copies of this for doing experiments. And Dr. Chain's expertise, she sometimes refers to it as droplet engineering. She also will call these little droplets, which are 15 microns in diameter, sort of mini petri dishes or culture dishes. And so you can imagine doing biology. These are cultured bacterial cells that are being imaged here. The parallelism that you get with this and the amount of information you can get by doing these experiments in parallel in this droplet-based system is phenomenal. So the key processes that we, through the MMF, can offer to support this is building, for instance, Su8 molds, the masters for doing the molding. We also have Dr. Nakagawa's group, and several groups have expertise with PDMS casting. So we can connect new users with people who have those capabilities. And PDMS to glass bonding and interconnects. So these are all the bits and pieces you need to put a system together to do an experiment. This is Dr. Gerlach's work. So we talked about bonding and compared to soft lithography or soft microfluidics, you might call this hard microfluidics. In this case, his group was developing flow cells to study biofilm formation and subsequent mineralization and how that depends on pore size. So one way to study that is to build structures that have controlled pore sizes. For instance, this silicon substrate has been etched. We've got these pillars. And then in order to make a closed flow chamber, the silicon substrate, which is the gray part in the back here, is overlaid with a glass cover slip, which seals it to make a closed cavity. So there's a bonding step there. And we don't have a silicon to glass bonder here. And so this work was actually done at the University of Utah. So this is an example of where we helped do the lithography, the patterning, and then there was a step where the users had to go and use a facility, a sister facility at Utah. Brian Bothner is here as well. This is another example of what I might call hard microfluidics. So the key feature here, this is a sample separation stage to prepare a sample, an unprepared sample like saliva, for instance, or blood, and prepare it for mass spec, and with just a simple one step. So this spiral channel here causes a mass separation due to the flow, and so then the outlet from here would be fed into the mass spec for further spectroscopy, mass spectroscopy. So in this case, the key features are a thick layer of permanent Su8, and your group might have liked this laminated film because, again, the uniformity of the thickness of the Su8 it can vary by a few microns once you get up to 25 microns thick, as this was. We've also got activation of surfaces for subsequent bonding of a glass overlayer. So we've got the tooling and the expertise to do that. And we've figured out, not we, but the users who have this expertise can do the glass drilling and attach ports and whatnot to build these microfluidic structures. So some of my own work, we've been using Su8 as well as a structural material. So this is not microfluidics, but it's the same basic permanent epoxy Su8. On the left is an example of a mirror that Sarah Lukes, who's here, built. And the key features here, this is a deformable mirror. It's a freestanding membrane of Su8 that's several millimeters across. But the membrane itself is between 1 and 2 microns thick. So we're using a material called Su8 2002. And you'll notice there's little features patterned on the surface. So we've developed recipes that allow reliable patterning of 4 micron holes through that Su8. We use those little holes to subsequently etch the silicon from underneath so that we leave a freestanding thin film of Su8. So this is gold coated. The shiny part you see is gold on top of the membrane. But we don't have the dry etch chemistry here at the MMF to do this final etch step. So Sarah went to a lab at University of Michigan, the Lurie Nanofabrication Facility, where they have a xenon difluoride etcher. Xenon difluoride is an isotropic silicon etchant, and it'll remove the silicon from underneath, accessing through those little tiny etch vias. And the important part here is that you know, because Sarah was trained in basic fabrication here and in all of our tools and safety protocols, it was fairly rapid for her to be trained on this one specific tool at Michigan, get her etch done, and get home again. You know, it's a matter of a couple of days in the lab, and then you know, this is an example of an effective way of doing that. On the right-hand side is another mirror that Timbo Liu has made recently. This is similar to the mirror I just showed you. It's got this thin film of Su8. It's about 4 millimeters across. But if you were to zoom in on the edge of this, you'll see that it's actually a thin film of Su8, and it's in a gimbal structure, meaning I've got a center plate that can rotate, and the rotation is controlled by a hinge here. And this hinge has electrical contacts coming across, but this is a mechanical element. This also is Su8, but in this case, it's thick 25 micron or 30 micron thick Su8. So just showing the types of features we can get with this particular material system and the expertise that we have in-house to support this kind of fabrication. And for this device, in addition to these various thicknesses of spun cast Su8, we also did a xenon difluoride etch, but this time at Cornell. So, you know, we go where it's convenient and where we can get access, and we can help users understand where they might go to get these processes done. Shifting gears from Su8, now I just want to talk about another etch process that we have developed for the inductively coupled plasma etcher. So the point I'd like to make here that's important is this nano-textured surface of silicon. So this used to be a shiny surface of silicon, but with the right process parameters, we can make an unmasked film. There was no lithography done here. We just put bare silicon in the etcher, ran the etch, and we get this very rough surface. Now, why would we want to do that? Well, the application is shown over here on the right. This is called black silicon. Turns out these nano-textured structures, which range from a few nanometers to sort of micron scale, are very effective light absorbers. And so we're using it because of its black properties. In fact, when we measure the specular reflectivity from this black layer, which in this case we've used as an aperture around a micromirror, the reflectivity is less than 1,000th of 1% specular reflectivity in the visible. So we get a very dark surface, and you can compare to the shiny silicon of the device on the left that did not get this treatment. Okay, so we've got some expertise there as well. So Phil, in a few minutes,
I'll just very quickly go through this. So some of the other work we've been doing since the inception of the lab is thin film coatings. In this case with Dr. Gannon, who's doing a lot of work with solid oxide fuel cells initially. And primarily we were helping him with, or he helped us in fact, and we helped each other with reactive sputtering processes where you would bleed in oxygen or nitrogen, react it with your titanium or aluminum or whatever you're trying to coat. And also a material that he specifically was working with Roberta Amendola was a yttrium stabilized zirconia. Ended up using an evaporation tool for that, have a residual gas analyzer so we could actively control partial pressures of oxygen. And maintaining that, we would maintain the oxide characteristics of this YSE material. Otherwise, it outgasses the oxygen, becomes metallic. So that's the kind of processes that we were able to working with Dr. Gannon, developed in the lab and now offered other people. Another project we did was with Oak Ridge National Labs, doing an alloy, testing alloys, in this case for corrosion passivity of magnetite coatings. And we have a couple examples here of magnesium titanium with a stoichiometry of 35% magnesium, 65% titanium, 65% magnesium, 35% titanium. Obviously much different film as it's grown. And as you can see in a bigger picture, again, as this film grows through the alloying nature, the stoichiometry is much different. The way we're able to know what the stoichiometry is with the XPS. His students went over to ICAL, and with the help of the ICAL staff, able to then take this data from the XPS, go back to the sputter system, adjust parameters until you get the alloy that you wanted. So the co-sputtering capability combined with having XPS and also use the XRD in this project allowed us to do this work for Oak Ridge National Lab, which was a nice project. And then final, I guess, mission of the lab, besides the research for academic industrial users, is education as a component of the university's mission. And I'm going to let David, as a professor, step in.
Yeah, in the last few minutes of the webinar, I'd just like to re-emphasize the importance of education as central to the mission of the facility. And Dr. Kaiser is here, and he uses the facility for as a regular portion of a semester-long class. So students will be in a lecture for a couple of lectures a week, and then they're in the lab for a few hours each week building devices. So one example is EELE 407, Introduction to Microfabrication. This is a class that teaches not only the basics of how we build things, but also the basics of electronic devices. So the students are building resistors and diodes and transistors. They're learning about them, then they build them, and then they get to test them in the lab. And in fact, the image that you see here is you know, a wafer on a probe station, and this is what you can see through the microscope with the 4 probes, and we're testing a little transistor or one of the structures on the wafer there. Another class, also a semester-long class, 408 photovoltaics. So this class now emphasizes PV technology, photovoltaic technology. So the students are learning about the importance of renewable energy while learning the technical details, and then they get to get in the lab and build their photocells and characterize them with a calibrated solar source. Another example. And the third class, another semester class, this is a graduate level course on MEMS and sensors and actuators. So again, students are learning now about silicon, the material, a little more detail about the material, both electrical but also mechanical properties of silicon, and learning about different types of sensors that we can build or actuators that we can build. And again, they get to actually make some devices and measure their performance throughout the course of the semester. In addition to classwork, education is happening every day with the students that are in there learning the tools, mentored research, and it's not only the students, it's also the staff that's learning, the PIs are learning, the users who are coming in from our industrial partners are learning. So education is certainly key. It's a lot of one-on-one education in the lab. This summer, we're going to have our first cohort of REU students coming to campus. This is a partnership between the Electrical and Computer Engineering Department and augmented with some funds from the NNCI that will be putting some students in the lab this summer. They'll be coming from across the country. And just a shout out to Todd also, he's taken this photovoltaics class, packaged it into a 1-week super course that we offer to science teachers who come to campus in the summer. They're pursuing a Master's of Science in Science Education. And in the course of a week, they'll be in the lab, they'll build these photovoltaic wafers, and then they get to take those back to their classrooms. So they are then exposing their junior high and high school science students to the excitement of photovoltaic technology, nanotechnology, and general science, and the things that we can do with it. So I'd just like to reiterate that this lab is driven by our user needs. It evolved out of user needs that existed before the lab existed, and we continue to evolve to reflect the needs of new users and the evolving needs of existing users. So we have a committee that evaluates requests and ideas and tries to prioritize needs, and so you just need to make your needs known to us, and we'll get that conversation started. Along those lines, we do have some proposed new capabilities that are coming online to support some of the microfluidics soft lithography capabilities. I want to say a couple of words about this slide.
Sure, yeah, so we have the soft materials research becoming more active in the area, and as part of this, I was working with a chemical engineering professor and using UV epoxy to make microfluidic channels as in-class demonstration modules, and we actually have a paper in ASAE for this. And this is the type of thing we're trying to build a portion of our facility that we would convert into this type of soft materials work. The needs are different for the environment. It doesn't need to be as particle free. You don't need the temperature humidity control. So I think we can do this much more affordably than the primary fabrication facility. So we're hoping to get this new lab built in the next year, I hope. Another tool under consideration is a new evaporation system. One possible component that is under discussion, one is ion assist, which would be nice to have, extending the energy range of our evaporated material. Also a glancing angle deposition technique that was being discussed. We can actually grow nanostructures. So rather than subtractively via etch process forming nanostructures, actually grow them on a substrate. Typically in either ordered or disordered with different, and sometimes some very complex structures just by coordinating their deposition rate with the rotation of the substrate. This has been worked out by a professor at University of Alberta, I think, who's one of the leading pioneers of this work. So that's just one of the things that's under discussion, and it will be further pursued as the summer progresses, should funding become available, to see if this is something of primary interest or if it's something we need to wait on. So,
okay, so just a little bit of the details. How can you become a user of the MMF? It's actually very easy. It should start with a conversation. So send an email to me or to Phil, and we'll set up a meeting either by phone if you're not local, or if it is easy for you to be meeting locally, we'll meet. Maybe many meetings depending on the complexity of what you're contemplating doing. It's a give and take, a back and forth. But once we understand what you need, we can help you decide how best to accomplish it. From that point, a registration form for the users and a project information form, and then we'll coordinate with you to get you trained, get your users trained, your students trained, and get you in the lab. I want to state again that we do have user grants available. So for new users of the facility, as well as external users of the facility, NSF is providing seed grants to help initiate those projects. If you're coming from outside the Bozeman area, we also have housing assistance. Heather Rouser is the person to contact, and we'll help you find housing, and also there's some financial assistance for that as well. So just to summarize, the point is the MMF has evolved to meet the user needs that are here at Montana State. We're here to help our users and PIs be productive, also be creative, and we want to have that conversation. Between the staff and our community of users, we've got a variety of expertise available, and we're here to try to make that accessible to you. And I just want to say that we remain responsive to this evolving needs. So if you don't find what you have now, start a conversation. We'll see how we can meet your needs. So this is your facility, MONT, and MMF within MONT is here to serve your needs. So we'll stop there. We'll take questions, but I would ask that the people in the room do the paper version of the webinar evaluation, and people remotely, the link is here for the online evaluation form. So we'll open it up for questions again now. Thank you very much for your attention.
Thank you.
I just have a comment. Could we advertise also our summer all users meeting?
Yes, I don't have the date in front of me. Do you have it?
I think we're
I think you're right. Okay, so we're advertising the MONT users meeting. This is for all MONT users, which includes MMF users. It will be here on campus on July 12th. So put that date on your calendar, and we'll get details as to where and the specific times soon onto the webpage. Any other announcements or questions? Any questions remotely? Okay. Thank you all for coming. It's been a pleasure to talk about the MMF.
Thank you.